Hi everyone. In this video we're going to continue on with an introduction to classification, and actually we're going to finish those slides. Where we left off was with k nearest neighbors, and we left off with this visualization. So the k nearest neighbors algorithm picks the k nearest points to a said point on the parameter space, and each point that is the closest, the k closest, each point gets a vote, and the majority wins. Okay, and so um, you can pick. The important part of k nearest neighbors is the choice of k. So how many of the nearest points are we going to use? And the choice of k really affects, of course, how the algorithm behaves, how the model behaves. And so we see in this picture here, um, the dotted line is the Bayes classifier, which is the sort of optimal theoretical classifier. If we knew, it can be calculated sort of only when we know uh, the truth. Okay, and so we never really actually know the Bayes classifier, but that's our gold standard, what we're looking to do. And so in this example, we do know the truth, but if we use k nearest neighbors with k equals 1, we get the left picture. And so we see some really nonlinear boundaries because we're only picking the nearest point. And so when you have that overlap, um, when the overlap of data, when you have some blue points in yellow and some yellow points in blue, then you get some weird boundaries. Although it's not too terrible, really. Uh, and then you go to something optimal, which is like k equals 10. You see that mostly gets rid of the weird boundaries, the weird circles of just a point. Um, it's still very non-linear, so it's not a curve or a line, but it does, out of these three, looks to be closest to the optimal boundary. And then if you see k equals 100, if we take k too high, then it's just going to turn almost linear. Or in fact, if you take k high enough, it will probably turn linear or something like that. And so we've sort of overfit, or we've uh, chosen too high of a k to be effective there. And so the choice of k, all this to say, the choice of k is important. Okay. And so how would we do that in R? Just like LDA and QDA, there is a function called, for LDA and QDA, we had lowercase LDA and lowercase QDA in the mass package. And now we have KNN. Okay. And so it comes from the class package. So again, it's not loaded into base R, okay, but you can load it with a package. There are other functions and other packages that do k nearest neighbors, but this tends to be a more popular one, and so I'll show it to you here. The big thing to remember with KNN, or this specific KNN function that we're going to look at, is it takes in the data very differently than LDA and QDA, which is unfortunate because LDA and QDA took in the data just like the LM function and the GLM function that we're used to using for linear regression and logistic regression. And so that was nice. We had a nice common syntax that we were using. KNN is not like that. So it's very picky about how it likes the inputs of the function, and it doesn't use a formula syntax. And when I mean the formula syntax, I mean the tilde in between the response and the predictors. So what the KNN function actually requires is a training and testing data set. And so we've talked about training and testing now. And so it requires this training and testing the true classifications for the training data and the choice of K. So it requires a lot, but we'll see how to do that. And furthermore, so I guess what's important for this is you don't really, unlike the other functions, LDA, QDA, LM, whatever, LM, GLM, you don't give a response tilde predictor. Like I said, it doesn't give the formula. You supply the predictors by supplying the data, the training data and the testing data, that only have the predictors that you want in the data. So you can't feed it the full data set and then tell it only which predictors to use. You need to feed it the data set with only the predictors that you want. And then that's a big change. So here's how you could do it. Here's an example with the Penguins data set. So I need a training and testing data set. And so with the Tidy Models suite of packages, it's very easy to do. Okay, I define how I want the data to be split up. And so I do that with the initial split function. I feed it the data, and then I tell it what proportion I want in training, and then the rest will go in testing. So I say I want 90% in training. That's going to create, that's going to do the split. It creates an interesting object that's hard to work with, but you can use the training and testing functions like you see right below it to actually sort of pull out the data from the split object. Okay, if you just try to work with the split object, which we created in line 1, it doesn't work so well. It's got a weird format that you're not used to. But if you use the training and testing functions on that, then it's going to pull out the data frame, and you're used to that. Okay, and so then next line, KNN, or next set of lines, and this is where you actually run the KNN function. And so, as I said before, it's a little weird, or it's definitely different than what we've seen before in a number of different ways. One that I didn't mention, but you can see here, is that the output of the KNN function is the predictions. So before with LDA, QDA, LM, and GLM, you fit a model and you had this like fit object and then used the predict function to get predictions. The KNN function doesn't give you a model, so to speak. When it runs, it gives you actual predictions. So again, something different. So you see in train and test, so it has 4 arguments that you need to give it: train, test, CL, and K. Train is your training data, and so you feed it the predictors that you want. Just the predictors, nothing else. And so I'm doing some interesting subsetting here. Maybe not interesting, it's fairly simple, but I'm subsetting my training data to only look at columns 3, 4, 5, and 6, because those are the predictors that I want to use. In testing data, I'm again looking at columns 3, 4, 5, and 6, because those are the predictors that I still want to use, and I don't want to use different predictors in training and testing. Okay? That's not kosher. And so I've got my predictors, only my predictors for train and test. Third argument is CL, which means the class, so it needs to know the truth for the training data. And so you'll see I supplied there, although I just noticed now that I misspelled train as TRAIN instead of TRIAN. Oh no, never mind. I'm sorry. I'm just going crazy. It looks odd to me. But anyway, so train data train underscore data is my object training data, and then species is of course the response that we're looking for with the penguins data set. We're looking ultimately to predict the species of the penguin, and so I give it for the training data the truth, and so it trains the model, then tests on the testing data, and then goes about its predictions, or it predicts. So the predictions that you see at the bottom of the slide are on the rows that were in test data. Okay, so it's going to train on the predicted data, test on the testing data, and then the predictions that you get out are what it predicts for the testing data. All right, and so the last thing that you need to supply it with is, of course, the most important part, the K. So the K and K nearest neighbors. I just chose 5 here, just because. Okay, and so then you get some output here. And so that is how you use the KNN function. It gives you the predictions right away, so you don't have to call an extra predict function on the output of KNN, which is nice, because just KNN works differently than the other ones. Okay, now it's important, or the choice of K is important, and so, as I've said many times before, and so here's a small function to do cross-validation, in a sense, for different values of K. Okay, so I took what I did in the previous slide, specifically the KNN function. So I did my training and testing. I kept that the exact same. Okay, and then I made a function that takes in the same stuff, but now I can vary K. So my function takes in one argument, it's K. I defaulted K to 5, but it can be something different. And so then you'll see at the bottom of the KNN function, I just say K equals K. And then afterwards, I say I have an extra line here that's an interesting one. Mean of preds equals test data $species. Now, for the KNN function, it didn't ask for the testing data species. It predicted that. But in reality, we do have that truth. We do have that species for the testing data, because how we split the data. And so what I'm doing here in the last line, I'm going to say preds equals test data $sign species. And so what I'm doing here is I'm saying, was that prediction equal to the truth? So did I get the prediction right or wrong? Unlike regression, where you're interested to see how far, what distance, what was the distance between my prediction and the actual value. For classification, you're either right or you're wrong, because there is no such thing as a distance between a Gentoo and a chinstrap penguin. So you're either right or you're wrong. And so preds equals test data $species is going to give me a bunch of trues and falses. Okay, it's going to give me a bunch of trues and falses, whether or not the prediction was right or wrong. So true is right, false is wrong. And if I take the mean of a bunch of trues and falses, so this is something that I use a lot in this class, and so it may look weird at first, but hopefully once I use it a bunch of times, it'll make sense. The mean of a bunch of trues and falses is the proportion of trues. So when I try to run the mean on Boolean operators, trues and falses, it's going to say that doesn't work. And so it's going to try to change the type of the things that I'm inputting to mean, so that it can actually take the mean of them. false changes to 0, true changes to 1. And so I have, now instead of trues and falses, I've got 1s and 0s. Okay, the mean of a number of 1s and 0s is the proportion of 1s. Why is that interesting to me? Or why does that matter to me? That gives me the proportion of correct decisions made. And so that's what really matters here. I want a K that's going to give me the highest, what we'll call classification rate. And so if I can classify, 100 points, 100% of the points correctly, that's the best I can do. And so I'm looking for a higher proportion. Higher proportions are better. And so in the next line, I use some functional programming that we talked about before, but I take this classify function and I basically plug in all k's from 2 to 33. Okay. And so then when I do that, I get the proportion of correct decisions for each of them. And so you'll see that the numbers are, there are some repeaters, and the numbers do change a little bit, but it looks like the highest proportion is going to be k equals 2 or 3. Or down here, like 13. Okay, which gets us to method evaluation. How do we actually evaluate whether a method is good or not? So I taught you all about LDA and QDA and KNN. How do I, for a particular data set, see which one is best or which ones are better than others? There will be different situations where each one is better. And so previously we've been using the entire data set to train our classifier and regression models, but that's optimal. That's suboptimal. We talked about this a little bit before, so we've got training and testing, okay, which is great. Now, this is the important part. For regression problems, we have metrics like mean square error and root mean square error that give us a tool for evaluating models. So for regression problems, we want the lowest mean square error, okay, because that tells us that the lower the mean square error, the better the fit. Lower error is better because error is the distance, vertical distance between the model, the predictions of the model, and the actual value. And so we want that, the vertical distance between the point and the line, to be smallest. And so that gives us a tool, a great tool for regression problems. But as I mentioned before, for classification, there's no such thing as distance between categories. And so what we're going to use instead of mean square error is what I'll call accuracy. There are a few different measures that we can use, and we'll see from time to time, but the standard one is accuracy, the percent of correctly classified observations from the test set. This is exactly what I was doing in the last slide, or last slides, with KNN. Okay, and so to do that, or what the output you'll usually see when running a classification model, is something called a confusion matrix. Okay, and it's not meant to confuse you. It is actually a little confusing why it's called a confusion matrix. But a confusion matrix is a cross-tabulation of actual and predicted classes. Okay, and so you see the confusion matrix down here at the bottom. Okay, the rows of this confusion matrix, the rows of the matrix, corresponds to what the model predicted. So you'll see it says prediction, and then below is Adelaide, Chinstrap, and Gentoo. So those were the predictions. It predicted into either one of those three classes. And then on the columns where it says truth, and then below Adelaide next to that says Chinstrap and then Gentoo, those are the truths. Okay, those are the true classes that we saw. And so the 12 inside of the matrix says that there were 12 observations where in reality they were Adelaide penguins, and we actually predicted Adelaide for that. The two next to it said that there were two penguins that were Chinstrap penguins, but we predicted that they were Adelaide penguins. And then the two next to that says that there were two penguins that were actually Gentoo penguins, but we predicted Adelaide as well. And so same goes for all of the rest of the points. Okay, so there were, what we're interested in, or what we want to happen, is we want to have large numbers on the diagonal, because we want to get it right. And so we want to see that, if in reality you're an Adelaide penguin, we want you to predict, or we want to predict that it was Adelaide. And so we see 12 is good. For Chinstrap, there weren't that many. In reality, there weren't that many Chinstrap penguins in the data set, in the testing data set, but we got 3 right there, so 3 Chinstrap and Chinstrap, and then Gentoo penguins, we got all correct. If you remember, Gentoo penguins really stuck out based on the different measures, and so it's easy to classify a Gentoo penguin, but we got 10 out of 10 right. Or rather, we didn't misclassify any Adelaide or Chinstrap as Gentoos, but we did misclassify some Gentoos as Adelaide and Chinstraps. Okay, and so that's a confusion matrix, and we're going to use a confusion matrix to calculate our accuracy. And so to do that, we just do the sort of cross-validation kind of thing that I did on a few previous slides for KNN. And it turns out that for this particular data set, that LDA and QDA have between a 97 to 100% accuracy, which is really good. And KNN has an 88 to 92% accuracy for optimal K. And so for this particular data set, LDA and QDA tend to work better than KNN. Okay? But I guess to keep in mind, KNN offers a lot of flexibility and nonlinear boundaries, which may be better in other circumstances where the data looks different. Okay, and so that is all that I have for the slides. I did also update the classification Scratch document on D2L, and that will hold, or that holds a lot of the examples of code which make the plots in these slides, but it also shows you how to fit the models both in Base R and in the Tidy Models suite of packages. So you want to take a look at those. It focuses on logistic regression, but it does mention how to do LDA, QDA, and KNN in sort of the Tidy Models framework. So you'll want to check that out, and we'll talk about that in class, hopefully on Wednesday.